Well, we made it this far, guys. So, as I've talked with most of you, I'm going to have to reschedule the final. Let's make it Tuesday instead of Wednesday. And to stay with the set final times on Tuesday, we'll go 10:30 to 12:20. With calculus being 5 days a week, we can kind of be a little flexible since there won't be any other class in here at 10:30 because I'm in here with Calc 1 on Tuesdays and Thursdays and Monday, Wednesday, Friday. So we know we're not interfering with another class. Okay, so what you can expect, I will allow you one sheet of paper like usual. In the 8.5 by 11, that's inches, not feet, not meters. So both sides. Get my units on there so you don't count me off one. For the final, we will have 15 problems, which is actually probably more than your usual tests. Although some of them have been a little bit longer, but not going to be a whole lot of any one particular topic, but just a little bit of everything. I would say 3 to 4 problems from each unit. So today we'll take a look at what to expect and the best way to study for the test. Look at your unit exams. One other thing I forgot to mention, I will provide the integral tables. So you don't have to worry about trying to remember those or write those down. Okay, test by test. We'll take a look at what we covered in test 1 and go from there. We began this unit with L'Hopital's rule. L'Hopital. Calculating a limit, and we looked at a lot of different ways to do that. But like I said earlier, there's not going to be a lot of anything, just a little bit of everything. So probably one limit to calculate using L'Hopital's rule. Then we kind of introduced some new functions and looked at the derivatives of those functions. So derivatives of logarithms of different bases, and also with the logarithms to rewrite the logs with the log properties. We got into that a little more extensively as we looked at logarithmic differentiation. So you may want to make sure you know the log properties, logarithmic differentiation. Those are just too big of words for me, especially on a Friday. We also saw the inverse trig functions, arcsine, arc cosine, arctangent, derivatives of those. And one of my favorite set of functions, the hyperbolic functions. Yay! Weren't those fun? Anyway, we introduce those in here as well. And so find the derivative of all these different types of functions, and kind of a special case was that logarithmic differentiation. Then we also looked at the antiderivatives, which is just the derivatives going backwards. Be able to find the antiderivatives of all these different functions. But like I said, the tables will be provided, so this would be definitely a place you would be able to use the tables. Now later on there will be some problems where you're not going to be able to use your tables. Well, you could use them, but I'll count it wrong if that's all I see. You got to show your work on those. But on something like these problems from test 1, using the tables would be fine. Sometimes you have to use some substitution to get it into the form to fit into the table. It's not like my book with 600 different forms where you don't have to use substitution much for that one. But we're limited to, I can't remember how many, less than 100 anyway. There's some substitution you'll have to do. So that was pretty much test 1. Really the new functions, or the more complicated functions that we introduced, derivatives mainly, but then the antiderivative forms that came about because of those. Okay, test 2. We saw all kinds of different integration techniques. This is where you're not allowed to use the table. Make sure you show your work, go through the process. But we saw a lot of different problems involving trig identities. And the main one there is your sine squared x plus cosine squared x equals 1. Manipulating what's given to you to be able to get it to a form you can integrate. Integration by parts. I guess along the same lines of trig identities is the trig substitution, although those types of problems look completely different than the trig identities from the beginning. Substitution. We saw partial fractions. We saw one thing that you may have to do before partial fractions is long division. And that happens anytime you have the numerator, the power in the numerator, to be greater than or equal to the power in the denominator. If that's the case, then you got to start out with long division, then perhaps it'll change to one part of it needing partial fractions. I know we saw that a little bit in this unit. And I guess the other type of problem I was thinking of is using the integral tables to find the antiderivative of something. So that will be well stated, so you do know you're able to use the integral tables. And these will be under the heading, do not use the integral tables. Show your work, probably bold and lots of exclamation points, just to make sure you know what I want. So that one, a lot of different things to look at there. Just make sure you're prepared with your note card, and this shouldn't be any too difficult for you. Questions on test 2? Test 3, we look mainly at a lot of applications, but we also introduce the improper integrals and see whether or not an improper integral converges or diverges. Definitely if it converges, we'll be able to say it converges to, if the integral equals 5, then converges to 5. So make sure you know how to do those. Improper integrals, there's a couple different type. Possibly if we have an integration that goes to infinity, that would be one type. Or if there's an improper integral, and I'll just throw one out here. Why would this one turn out to be an improper integral? Okay. It's not defined at x equals 3. So to work this out, we'd have to integrate from 0 to, well, technically 0 to b as b approaches 3. But notation-wise, we can kind of show that. I guess we're looking at this particular one. And then go through the limits and integrate and so forth from here. This is not a real interesting one because I think it will diverge pretty easily. We can see that, but anyway, that's something you've really got to watch. At x equals 3, we have an undefined function. So some of those you look at it like, why would that be improper? Well, that's why. This one's pretty obvious. If it goes to infinity, that. But the others, not so much. A little bit more work to do with those. Okay. Now, we started the applications with the volume of a surface of revolution, or a revolving of a revolved region. I guess we can say it that way. Maybe not proper English, but I don't teach English, so it ain't gonna matter. But take some region, revolve it around the x-axis, y-axis, x equals 3, y equals 2, something like that. And these problems, we looked at two different techniques. Some problems, both techniques work. One technique may be easier than the other, but definitely there will be some problems where disk method would be easier. Some problems, the shell method would be easier. And once in a while, only one technique actually works. But most of the time, both of them work. It's just a matter of which one do you see, which one's easier to work through. And the disk method, there might be a region where it has a hole in the middle, so you'd have the pi capital R squared minus the pi little r squared, and you got to figure out your big radius and your little radius. So volume, we looked at several examples there, so probably one of the applications is going to be that. Maybe just one problem. Again, out of those 15, I'm not going to put too many volumes on there. Next topic we looked at was the arc length. Well, that would be the arc length of just some curve. But then we extended that to surface area. Take this curve and revolve it, maybe about the x-axis, and find the surface area then. We get a three-dimensional little shell there. So arc length was what? A to B of take the derivative, square it, add 1, then take the square root, which got really ugly algebraically. And then surface area, just extend that a little bit. Let's see, about the x-axis here would be 2 pi, well, we'll do in general, 2 pi r, and then the ds part, the arc length part. So the r, in this case, the radius of our slice would be y, which is the function. We could keep it in terms of x, but if we revolved it about the y-axis, oh my, I think I'd flunked my art final today, but the radius here would just be x. We wouldn't need the function, it would just be the x part. The function would still show up in the form of the arc length part. So arc length, surface area, a couple very similar formulas. Make sure you know how to set it up. Next application we looked at was how much work a spring does in moving, compressing, or stretching the spring. Couple other applications as well with that. How much work is done by propelling something into space. How much work is done by emptying a tank or siphoning a tank out the top, pumping water out the top. So a lot of different possible problems for the work. But essentially, you look at force times distance, and then sometimes the force is variable, sometimes it's constant, and the distance is variable. Sometimes both are variable, so got to figure out what description allows you to represent those. Then the next part was the center of mass, or center of gravity, as we say in working with pounds. But density might be actually a function, not necessarily constant density, but density usually something like this. Maybe it's going, whoops. Okay, that's not what I wanted. Maybe the density is a particular function, or maybe it is constant, but density times area is typically how we find mass. And then that kind of extends from there. The moment of a mass, we use distance times mass, or actually distance times force. We do put it in terms of force, but that is just multiplied by another constant. But your formulas, x bar If it's a region in between two curves, that would be for the moment, and then over the mass, that would be for the denominator of x bar. The numerator talks about the moment. The denominator is basically your mass, which you kind of can limit if it's constant density, just limits to the area between those two curves. And then y bar, well, we developed a different formula for it. Denominator is still the same, but the numerator, you remember what it is? One half times the top one squared minus the bottom one squared. So maybe find the x bar, y bar, center of mass, center of gravity, however it's defined there. Use these, and it gets a little involved with calculations. Just be careful, watch your signs, don't miss a negative somewhere, those darn little dashed lines. Okay. And let's see, the last application we looked at was fluid force. And for fluid force, we would say, well, how much force is on a vertical plate submerged into water, or let's say there's that. I think our problem on the test had a triangle so far down under the surface of the water, and then fluid force, the formula for that, we'd take a slice, the depth under the water, the deeper it is, the more pressure there is. Pressure was depth times what, area? So the WHA is our formula. W would be the weight density. So water, that was your 62.4. 9,800 was newtons per cubic meter. 62.4 pounds per cubic foot. So the W, though, that's just a constant. I will give you the constant, the water constant, or may not be water, whatever the liquid is. Most likely it's water. Then your H is your depth, and then the area. Well, depending on the depth, the area, that's going to vary, so we've got to figure out the formula for the area, and then of course we integrate from wherever to wherever. So total fluid force on this submerged plate. Okay, so lots and lots of good applications, and again, you're not going to see one of every type, but probably 2 or 3 of those, depending on which type I decide. Okay, then we jumped into sequences and series. What we'll focus on here, don't worry about sequences, so just the series part of it, but definitely probably a few problems of, does this series converge or diverge? And you can bet I'm going to ask for the details, not just 50-50, oh, this one converges. Might be a problem, find what it converges to, which would be limited on the type. That type would either be the telescoping or the geometric. So the other tests that we use, we could tell whether it converges or diverges. We just couldn't say it converges to this. Later on in the chapter, after the test, we started to see where things converge to, or why it would converge to e squared, but we're not going to worry about that for the final. Again, it'll be like the problems on the test. Determine whether the series converges or diverges, state the test you use, conditions that are met, and so forth. So, and on those, there may be more than one test that works. I'm not going to count you off if you use a different test than what I use, but just use the test correctly. Limit comparison can be used almost on every problem, almost. Now there's some that you shouldn't, but you still could. Some of the obvious ones you hopefully recognize what to use it on. So that's more what the final will be. Which one are you going to use, and can you show that it does converge or diverge by those conditions? So we also looked at alternating series and whether, kind of an extension to this, does it converge conditionally or absolutely, or perhaps does it diverge? So something like that. If it diverges, well, we can't say diverges conditionally, it just diverges. Conditional would be convergence, so make sure you know how to show that. Okay, that is test 4. Any questions there? And then test 5, which that should be really fresh in your mind, hopefully. But conic sections, again, make sure you have all the formulas down and all the characteristics. That may be, here's the equation for one, what's the vertex, foci, center, or parabola's case, the focus and directrix, or perhaps, given these conditions, what is the equation of the hyperbola, ellipse, parabola, something like that. So a lot like the problems we saw in test 5, 2 different types there with the conic sections. Parametric equations, slope of the tangent line or concavity, horizontal vertical tangency, or what points have horizontal tangent lines, what points have vertical tangent lines. And again, goes back to your derivative. Arc length, one of those probably will just have you set it up and not worry about integrating. Those get really nasty. So parametric equations, main thing there, dy by dx and second derivative. Make sure you know how to calculate those, what they tell us, and then arc length formula. Polar coordinates, basically convert from one system to another, whether given rectangular, convert to polar, or given polar, convert to rectangular. And then some of the applications, slope of the tangent line, possibility there as well. Same idea that we used up here. The equations get a little uglier. X equals r cosine theta. Well, r would be the given equation. Plug that in and take your derivative. Y equals r sine theta. Go from there. And then finally, the area problems. Find area inside maybe the entire graph or a portion of the graph. Given the polar form. And area, it's not just f of x times dx, but it would be what? Okay, 1/2 r squared d theta. So don't forget that. I know you get to that point and you're like, but make sure you have that down on your note card, and that should help. So, any questions about the test 5? I have not had a chance to grade them yet, but I should have them graded by Monday. If you want to pop by either my office, or I'll be in here Monday, 10:30 to 12:30 with Calc 1 final. So I will have them graded by 10:30 Monday morning. If nothing else, we'll see you guys on Tuesday at 10:30 in, oops, not SMA, just SEM 207 in here. So, have a good weekend.